So we were talking about the comparison between the TXT and the DST testing, that is triaxial testing and the direct shear test. So, so the first thing is that there is uniform stress distribution in case of triaxial test, whereas in a direct shear test, the stress distribution is not uniform. So that is explained actually by this figure here. So, sorry. Okay, so if we look at this figure, so this is the TXT test, okay, the triaxial testing. So we can see that the stress distribution can be imagined uniform in this section here, and at the end we have dead zones because you see that we have porous stones at the top. Okay, so there is some shear between, and there is some complex behavior that is still unknown, so that produces a dead zone, so we don't have any stress here. Okay, and all the stress is almost in this range, but you can see that it is uniform throughout the cross section, whereas in case of a direct shear test here in the samples, you see that because initially we have a bend like this, but you know that the specimen starts to move forward. Okay, so that results in an unequal stress distribution. So same thing is mentioned here, that we have very complex stress distribution in the direct shear sample, because with the progressive sample, this area of contact between the two particles, it starts to change, because initially it's the whole box, and then with time when the upper box is moving ahead, then the contact area between upper and lower box starts to reduce, so that's why it changes results. Okay, so the second thing that is related between the two tests is that volume change measurement is more accurate in a triaxial test, and then we have complete state of stress is known at all stages of the triaxial test, whereas only stresses at failure are known in a direct shear test. In a triaxial test, the sample fails at the weakest plane, because if this is the soil specimen and if this is the weakest plane, it can fail here, it can fail here, or it can fail here. So it depends on whatever is the weakest plane, so it will choose according to that and it will fail accordingly. Whereas in case of a direct shear test, the only failure is going to happen along a predetermined failure plane, that is the horizontal direction. So this is a biggest flaw, because in real life this might not be the weakest plane and we can have a misleading result. Okay, so pore pressure can be measured in case of a triaxial testing, but we don't have anything to measure pore pressure in case of a direct shear test. So this is a little comparison between the direct shear test and the triaxial testing. Now moving ahead, let's see. Okay, so now we start to talk about principal stresses. So here is a little definition of the principal stresses, that through every point in a stress body there are three planes at right angle to each other, which are unique because they are subjected only to normal stresses. That means there are no shear stresses on that. These planes are called as principal planes, and the stresses that are acting on these planes are called as principal stresses. So just to make things easy, just remember that if in a plane we don't have any shear stresses, so that is a principal plane, and if there are shear stresses, then that means it's not a principal plane. So if to explain that, if I draw a same cylindrical soil specimen that we are using in a triaxial test, so you see there that we have a major principal stress on the top and we have a minor principal stress on the side. This happens on all the sides. So you see here that there are no shear stresses, no shear stress here, no shear stress here, no here, not here. So that's why sigma 1 and sigma 3 are called as principal stresses. And generally we have three types of principal stresses. Major principal stress is indicated by sigma 1, minor is indicated by sigma 3, and there is intermediate stress, that is sigma 2. Because we are doing with a circular soil specimen, so we say that because this acts in all directions, so we can say that sigma 2 is equal to sigma 3. So for our class purposes and for numericals, we will only consider the major principal stress as well as the minor principal stress. So the stress that has a large value is called as a major principal stress, and the stress that has a lesser value is called as a minor principal stress. And once again, remember that there are no shear stresses. Okay, if in the same specimen, if I draw it like here, and also this was sigma here, and sigma, we know that it's a normal stress. That means it is applied perpendicular to the surface. Okay, so that means this makes an angle of 90 degrees here. So that's why it's called as a normal stress, because it is at a 90 degree to the plane on which it is acting. So if on the same specimens, if we have some shear stress value here and we have some shear stress value here, so then there are no more principal stresses. Why no more? Because they have shear stresses along them. So by definition, we should remember that a plane that only contains normal stress acting on it, so that's a principal plane, and the stress itself is called as a principal stress. But if the plane is accompanied with the shear stresses along with the normal stress, then that means that that is not a principal plane. Okay, so we have to remember these things because they are going to be used throughout in this subject. So in our class we stick to 2D, because as I told you here that we are assuming sigma 2 equal to sigma 3 because we are having a cylindrical soil specimen. Okay, so now we will discuss Mohr's circle of stress. So this is very, very important. It goes a long way in geotechnical engineering as well as in your future life. You might come across the Mohr circle time and again. So you should be understanding it very well that what is a Mohr circle. So Mohr circle is the representation of stress state in any element, okay, in a soil specimen, okay, on a graph, or it's a graphical representation. Now how does that work? So just taking again the example of this cylindrical soil specimen here that is being subjected to a triaxial test. So you see there is sigma 1 acting on the top and sigma 3 on the side. So according to it, you can represent the stresses by plotting like this. On x-axis we have normal stress, and on y-axis we have the shear stress. So it is represented by a circle. The center of the circle can be located by this definition here. It says center of this Mohr circle is sigma 1 plus sigma 3 by 2, and radius of the Mohr circle is sigma 1 minus sigma 3 by 2. So let's do that. So this means let's point out sigma 1. So let's say this is sigma 1, and sorry, this is because sigma 3 is minor, so it comes before. This is 0 and this is sigma 1. Okay, so the radius of the circle would be somewhere here, so that means this is supposed to be sigma 1 plus sigma 3 by 2. And then with this as a center, I will open my compass like this. Okay, I will open my compass and then I'll draw a circle like this. Okay, so now the radius, this is sigma 1, this is center. So the radius of this circle is sigma 1 minus sigma 3 by 2. So you see it's very easy to remember that you simply look for sigma 1, mark that value here, and then you look for sigma 3, mark that value here. First look for sigma 1 and then sigma 3, then sigma 1 plus sigma 3 by 2 is the center of the circle. Open your compass up to a radius of sigma 1 minus sigma 3, and then you plot the circle. So this is the Mohr circle, and it represents the state of stress in a soil body. Okay, all right, so moving on, so this is how we plot Mohr circle once we know sigma 1 and sigma 3. Okay, there can be a chance that we do not know the principal stresses on the soil specimen, okay, and we know other stresses. So then let's see how to draw in that case. Okay, so now let's talk about drawing a Mohr circle if we know the if you do not know the principal stresses. Okay, so I have already drawn some sketches here. So have a look at this particular specimen. Okay, so we see that on the planes of the element or the soil element, we have on horizontal surface we have sigma y and minus tau xy, and on the vertical axis we have tau xy and sigma x. Okay, so let's draw the Mohr circle with this. So if we have, this is normal stress on the x-axis, and on y-axis we have sigma n. Please remember that the sigma n and tau, they are supposed to be on the same scale. That means if one small box here means 10 psi, so also here it should mean 10 psi. Okay, so let's call this value, okay, let's call these values sigma x and tau xy as point p1, and call these values as p2. So same thing is mentioned here, that my point 1 is sigma x and tau y, that is the state of stress on the vertical plane. This is the vertical plane. And p2 is the state of stress on horizontal plane, so this is horizontal plane. So we have a sigma y and a tau xy. Okay, now we plot. So sigma x and sigma y both are positive, and shear stress that is on p2 is negative. And this is the sign convention that we have followed here. You have to remember this, that if we have counterclockwise shear, then we call that as negative, and if we have clockwise shear, we call that as positive. So based on the same analogy, so if we plot the points, so they are plotted as p2 is plotted here and p1 is plotted here. Why p2 is plotted below the x-axis? Because this is negative stress, so that's why p2 plots here, and p1 has positive stress, so it is plotted here. So we will join these 2 points with a straight line, and where it intersects the x-axis, this is the center of the Mohr circle. And then we will open your compass with the diameter from center to p1 or p2, and then plot the Mohr circle. Okay, so this is how Mohr circle is plotted with help of points or where we do not have principal planes. So just to jog your memories once again, let's summarize what we have just discussed. To further clarify that, if we have a soil element, okay, and we have normal stress here and we have normal stress here, as it do not have any shear stresses, so that means sigma 1 and sigma 3 are the major and minor principal stresses, because we do not have a shear stress. So let's plot Mohr circle for this. On x-axis we have sigma, and on y-axis we have tau. So first of all, I'll mark location of sigma 3, and then I'll mark location of sigma 1, and then I will locate its center, and that center is sigma 1 plus sigma 3 by 2. Okay, and then open my compass and then plot the circle, and the radius of the Mohr circle is sigma 1 minus sigma 3 by 2. So this was the case once we only have principal stresses, so it's very easy, just mark sigma 1 sigma 2, because there are no shear stresses, so that means the value of it is 0. Okay, all right. So if now let's plot this for so now we'll look at the second case. Once we have shear stresses along, so this is, let's say, sigma y, okay, and this is sigma x. Okay, let's check the sign convention. Okay, so I will plot this as minus tau xy because this is counterclockwise, and this as tau xy because this is clockwise. So I now plot, I have 2 points, I will plot these 2 points. Let's call this, sorry, this as p1, this as p2. So once again, sigma and tau. So p1 is positive, and that is sigma x. Let's say it is lesser and sigma y is more. So let's say this is point p1, and p2 here sigma y, just remember that sigma y is greater than sigma x in my example here, so that's why. So this means that the coordinates are, this is sigma x and this is tau xy, and then I'll plot point P2, and let's say it's plotted here, P2, and it has coordinates. This is negative, so this is again same tau xy but in negative direction, and this is sigma y. Okay, all right, so what we will do, we will join them with a straight line, and where it intersects with the x-axis, so that means that is the center of the Mohr circle, and then I'll plot a circle by keeping this at center. So this is the Mohr circle. This is how I plot it once I do not have principal plane values. Okay, so after this we have one important thing that is called as pole. So pole is why it is important, we call that as a pole of the Mohr circle, or we call that as origin of planes. According to definition, each and every plane in any element in the element will pass through the pole. Okay, so how do you find out the pole? So if we look at the example here, so if we look at the example here, so what we're going to do, so this is point P1. Now P1 is acting on a vertical plane, so I will draw a straight line from there. Okay, so I'll draw a line straight because P1 is acting on a straight line, so I'll draw a line straight from the pass. It is a straight line and passing from P1. And P2 is acting on a horizontal plane. These data is acting on a horizontal plane, so I will now make a straight line from P2 that passes through P2 and it passes. So now you see here that the intersection is intersecting on the circle. Okay, and this is called as a pole. Okay, now we move to the top example. Now sigma 1 is acting on a horizontal plane, so I will draw, this is sigma 1, I'll draw a horizontal line that is passing to sigma 1, and sigma 3 is acting on a vertical plane, so I'll draw a straight line from here. And where they are intersecting here, so that means this is the pole of the Mohr circle. All right, so why this is important? Pole helps us in calculation of lot of numerical problems. Okay, so it is very easy and it's very necessary to remember how to draw poles. Okay.